All right, so I want to start here by first making a quick comparison. We did a discussion about work. That's where we started in our last chapter. That work was the method by which you changed something's energy. So we started with the concept of work, and that work was done whenever a force caused a change in position. The amount of work was based on how much of that force caused that change. In fact, we went as far as to say that if there's a net force, this would cause specifically a change in the kinetic energy. Thus, the answer to the question about the rocket. The net force caused an acceleration. That acceleration caused a change in the kinetic energy of the system. So there's more energy in the system. Now, that being said, from here we were able to show that, well, net force equals ma. And if you remember what we did from this point forward, we reminded ourselves that we have a relationship that had 2a delta x in it, which is how we showed that kinetic energy is 1/2 mv squared. Right, we just did that substitution there, and that's where kinetic energy came from. Well, momentum's a lot like that. Momentum can be derived this way. And so for the next few moments, I want to talk about the derivation of momentum. So for you math types, this is really for you. You will not have to do this on any test. But if you understand the nature of what I'm about to talk about, it may help you understand what Newton was getting at. This is not Newton's second law. This is what we teach students about Newton's second law. First, Newton's second law is very directional. And although that's not a big change, this is still not really what Newton was getting at. Newton understood that physics was about change in motion. That was the most important concept to him. So everything was centered on looking for changes. When we talk about energy, we were talking about changing the type of energy an object or a system has. And work was the method, force was the connection. Well, if we consider that force for just a minute, we know that acceleration is really about change. It's about change in velocity. This is the definition of acceleration. It's the rate of change of velocity. So if you have a net force, you are causing a change in an object's velocity. Now, if you distribute the m, you get this other term in the numerator, one that to this point we've not really discussed. But this other term combines the inertia of an object with its velocity. Newton actually believed that mass and velocity were connected together, that there was something different about an object when it was moving than when it was stationary. Moreover, he believed that some objects acquired a different way of interacting with nature when they were moving. He called this momentum and used a lowercase p for it because that makes a lot of sense. I guess it was the only letter he had left. So, if you're not following this, momentum is the product of mass and velocity. We use a lowercase p for it. It is a vector, and it takes its direction from the velocity. This is the equation for momentum, and if you're asked to calculate an object's momentum, that's what you must do. Please understand that that's not very much. That's just multiplying two numbers together. But what Newton really said is that net force was about the rate of change of momentum. He wasn't about acceleration. That's how we have come to interpret it. Newton's original law looks more like this than MA. This is Newton's second law. He didn't want to be bogged down with the idea that an object's mass couldn't change, or that a system of objects couldn't change its mass. He believed in the concept that mass of a system could be a variable, not a constant, but also believed that that mass being combined with its velocity changed the object. Look, as an example goes, you might not like this one, but it really does prove a point. A bullet is not dangerous on its own. It's about the mass of a box of paper clips or less. It's the fact that it's moving at 300 meters per second that makes it dangerous. At the same time, a bus doesn't have to be moving that fast to be just as dangerous as a bullet. Understand that it's the momentum of those objects that make them dangerous. And it comes right back to this. The more momentum something has, the harder it will be to change it. That is the definition of inertia, but Newton didn't separate inertia from motion. We did, to try and teach it to kids. He knew that they were linked together, that the difficulty in moving an object was not just about its mass, but by a combination of its mass and velocity. That the more massive it is, the harder it is to change, and the faster it's going, the harder it is to change. So he called that momentum. That momentum is really a measure of an object's resistance to changes in motion while moving. Momentum is a measure of an object's resistance to changes in motion while moving. Yes, sir?
So it's basically the same as inertia, but when it's moving.
Yeah. Momentum is inertia while moving. I mean, if you really want to be a theorist here, you could say that zero velocity is a type of motion too, and say that momentum is inertia. But the truth is, it's better to think of momentum as inertia while moving. The more momentum something has, the more difficult it is to change its motion. Who's in calculus or has had it? Just a quick side here. Newton would never have written this. This is a derivative. That net force is the derivative of momentum with respect to time. Remember, Newton created calculus. He created differential calculus. Leibniz created integral calculus. And although they both work together, Newton's frame of differential calculus is the way he framed the way physics worked. If you look at his original work, almost everything is based on a derivative of something with respect to time or position. Now, we have extrapolated that to things like the gradient and the curl, which take this to 3 dimensions and have found different ways to formulate it. But ultimately, almost all laws that Newton came up with could be written as a differential. And although we won't use this at all, we will use this. This is the way you should really think about Newton's second law. Now, with the mathy math part, there's going to be math here in a few moments, and I'm going to stick with that math theme, but this next part, everybody has to know, okay? So let me start with where I ended. Net force equals the change in momentum over time. I want to clean this up and change this a little bit so that it kind of models the equation we had for work. I'm going to multiply both sides by t and write this as the net force times time equals the change in momentum. This function should look a lot like the definition for the Work-Energy Theorem. The Work-Energy Theorem was net force times displacement equals change in kinetic energy. These two things are not the same, but they are two sides of the same coin, in that using that metaphor, to truly understand a system, you must look at both. that they describe different parts of the system, and they should be used together. We tend to study one at a time, but to really understand what's happening and to understand what I want you to be able to do, you use them both. You consider how both are happening at once. An object whose momentum's changing is likely also changing its energy. But this relationship has a special name. It's called impulse. Impulse has two sides, two parts. There's the left side here, which is the cause, and the right side, which is the effect. When asked to calculate an impulse, you could be given information about either. They are the same. To cause an impulse, you must apply a force, and you must do so for some instant of time. But the effect of that impulse is to cause a change in momentum. Meaning, I can tell you what caused the change by looking at the effect. On the other hand, I can tell you what I would have to change about the force in order to get a bigger effect or a lesser effect. These two things, though, are both considered impulse. Impulse is either the change in momentum or the force times time. Both of these are impulse. Now, please be aware, the biggest mistake you make here is not recognizing that this is a vector equation. Meaning, direction is exceptionally important here. Let me give you an idea of what I mean. This is a starting activity. I want you to understand that in this activity, we're going to study several things. So I'll be coming back to this example more than once. But I'm going to start where I feel something simple. For example, if I drop a ball so that it hits the ground going 10 meters per second, the ball is likely to bounce off the ground. Let's say the ball bounces off the ground so that it's moving upwards at 7 meters per second. What was the impulse applied to the ball from the ground? Let's assume the ball is half a kilogram. Now, before you run away with this question, listen closely to the way in which I'm asking it. One of your problems is you're not reading the questions closely. I know that there's a lot of words in these questions. It's because they're trying to see if you're really paying attention. Let's see if you're paying as close of attention as I'd like you to be. I asked you what the impulse was on the ball from the ground, because I know that there must have been a force on the ball from the ground because they are in contact, right? The instant the ball hits the ground, there's a normal force on the ball from the ground. But by Newton's third law, there's also a normal force on the ground from the ball, which means that the ground experiences a force. In fact, it experiences the same force as the ball. And the ball can't be in contact with the ground for any longer than the ground can be in contact with the ball, which means based on our cause of an impulse, force, and time, there are actually two impulses happening at once. There's the impulse on the ball from the ground, while there's also an impulse on the ground from the ball. Because of Newton's third law, there's always two impulses. Always. There are always two equal and opposite impulses. This isn't a new concept. You do work on the table does work on you. It's the way energy is transferred. Here, momentum is transferred. So the interaction of force causes a change in momentum. So the takeaway here is that because we said earlier for every force there's an equal and opposite reactive force, for every impulse there's a reactive impulse. I asked for the force on the impulse on the ball from the ground. But I should also be understanding that in finding it, I'm probably also finding the impulse on the ground from the ball. Right? That they are together here. So, before I start this, because I indicated to you from the beginning that impulse and momentum are all about vectors, one of you should decide whether that arrow points in the positive direction or the negative direction. Just yell it out. All right, so we are now stating that up is positive. That's an important distinction now. When you're answering your question, you should be answering with the word up, or you should be making your answer positive if it's pointed up. And obviously, if it's downwards, the same will apply. Now, I asked for you to calculate the impulse on the ball from the ground, but clearly, I don't have any information about the force or the time, which means I can't get that information to you by talking about the cause. I probably could get that information to you by talking about the effect. I know everything about the effect of this impulse. I know the ball had an initial momentum and that eventually there was a final momentum. And between the two, there must have been something that caused this change. Now, calculating this kind of stuff isn't tough, guys. It's not the calculation that's hard. It's understanding that when they write this test question, they're probably going to ask you in a way that makes this more complicated than it seems. Because calculating the impulse merely is me punching in 0.5 times 7, because that's the final velocity, and me knowing that this is a positive 7, minus 0.5 times 10, and me recognizing this is a negative 10. And you guys understand that the difference between having that negative sign and not having that negative sign are two of your choices on the test, right? Because you know I'll put them both on there, and you'll rush through that test, you'll forget to take that into account, and you'll wonder why there are two different numbers there, but one of them matches the number you got, and you get it wrong. And then you're sitting going, I don't understand anything about physics. And I'm like, yep, you forgot a negative sign. And you'll make that feel like it doesn't mean very much. It was just one negative sign. You're right, but it's just one multiple choice question too. You get where I'm going with this? It's not hard to remember this, but you need to be deliberate. And on a test, you're usually in a hurry. And it might not draw a picture. They might just say it bounces off the ground. You'll have to infer a picture. Do you see all these little pieces that are there? Not to mention the fact that all I have to ask about is the ground and not the ball, and I have to shift everything in the opposite sign. There's a lot of little ways to throw you off the problem. You have to be paying attention to all of them, while at the same time still knowing that it's just delta P. You think knowing that is all you need to know for the test, and that's why you have trouble. Right? So, the actual answer here, I hope you guys put together, is 8.5. Did you get that? I know a few of you did, because a few of you already ran the numbers. I could see it. 0.5 times 7 is 3.5, and 0.5 times 10 is 5. The negative times the negative made it positive. The answer is explicitly positive, which means the impulse was upwards. Impulses have direction. Now, don't walk away from that. This was in kilograms. This is in meters per second. Okay, kilograms, meters per second. That is the unit of momentum and the unit of impulse. There's no special name given here. Okay, no special name. Now, some of you are really smart, so follow along here. You know that the cause would be newtons times seconds. Right, that would be the cause side, which means that is also a unit of impulse. But a newton is a kilogram meter per second squared times seconds. And I can cancel one of the seconds out, and I get a kilogram meter per second. So Newton second and kilogram meter per second are the same. Don't be thrown off when on the test you work it out and you get 8.5 kilogram meters per second, but the selections are 8.5 Newton seconds. Do you see why? They represent the same thing. That's a test writer trying to throw you off. Yes, sir?
So you can use Newton seconds for momentum as well?
Yep, they are the same. I will generally write kilogram meters per second, but that doesn't make it the only way, and not every physics teacher agrees with me. Now, if I had asked you what the impulse on the ground from the ball is, do you understand that that answer would be negative 8.5 kilograms meters per second? Okay? So that last prepositional phrase is the difference between a positive and a negative. Now, if I tell you the ball is in contact with the ground for 0.02 seconds, you should be able to tell me how hard the ball pushes on the ground. Do you understand the question? Let me say it again. If the ball is in contact with the ground for 0.02 seconds, can you figure out how hard the ground pushes on the ball? Well, that's the cause portion. Meaning I would now use this to figure out the force had to be 425 newtons. And it would be downwards, because the ball pushes downwards on the ground. All right.